Okay, it's my pleasure to introduce our next speakers. I mentioned yesterday, if you've looked at an earlier version of our schedule for today, Martin Meyer-Schellersheim was scheduled to talk, and unfortunately, due to a family emergency, he had to be away, and we were fortunate that Chris Barrett was able to step in. Chris is the Executive Director of the Virginia Bioinformatics Institute, where you're sitting, also Director of the VBI at the National Capital Region near DC, and he's a professor of computer science here at Virginia Tech. He got his master's in engineering science from the California Institute of Technology and a PhD in bioinformation systems also from Caltech. Prior to joining VBI, he worked for 17 years at Los Alamos National Labs, where he was a leader of basic and applied simulation science group and built up a research group active in theoretical, applied research methods, in terms of intelligent systems, distributed systems, and so on. His research interests include simulation of very large systems, as you can see from his title, theoretical foundations of simulation, computational and systems biology, and cognitive science and computationally aided reasoning. He's received several distinctions, including Distinguished Service Awards from Los Alamos National Labs, the Alliance for Transportation Research, and the Royal Institute of Technology in Stockholm. The title of his presentation is Measuring, Modeling, and Managing Massively Interacting Systems. Chris, it's a pleasure to have you here.
But what I'd like to talk about is, in a word, what we're calling here information biology, sort of the rationale for it, the need for it, how it relates to our history and hopefully our future and what you do. So this presentation was one that I actually put together, most of it. I mean, there's a few changes, for a PCAST presentation for the National Academy. And the topic of this particular session had to do with the use of big data in science and decision making. But even though that isn't what this is about, I think some of the stuff that goes on in here might be. And I'm just going to use it very loosely because I'm not going to really talk to this particular presentation. The reason I'm telling you that is I'm going to use some of the slides because I wanted to have some pictures. And they're in here. Okay, so the bottom line here can... So let me just ask a couple of questions and see if this is a way to, like rhetorical questions, to sort of motivate this thing. If you look at a honeycomb, are you looking at a biological structure or a technological structure? And if you look at the activities that the bees on the honeycomb is structured by the honeycomb that they made, are you looking at social behavior, biological behavior? Is the fact that all the bees in the beehive have the same genome relevant to something? Those kinds of questions have to do with how interactions, even among things that have the same genome, produce outcomes and structures and so on. I mean, it isn't entirely surprising, but I like this example. I don't use it. That the elaboration of which really can't be understood by studying and staying on the genome. It's simply impossible, but it's not necessarily the case that it's a good idea to say, well, that's, the biology, and then there's the other omics, but the rest of this stuff is social stuff or something, honeycomb physics. So it's not clear where the inside and the outside of whatever system is you're looking at there is, I guess, the point. Another example, I have a picture of this. I'm going to apologize in advance for flying around in here. Here it is. Here's the picture. Oh, crap. Sorry, too many button pushes. So I'm sure you all know about this, but I like the picture. In this case, we have certain locusts and certain grasshoppers that have exactly the same genome, and what happens is that when environmental stressors affect impose themselves on these grasshoppers, and it drives them into resource-limited environments or environments where the nymphs are in close proximity. It depends on a little bit on which grasshopper you're talking about. Very quickly, they start producing a morphologically very distinct creature. There's really nothing similar in terms of the armor on the insect, their leg proportions, their behavior is different. Even details of things like brain biochemistry and stuff are different between these two things, and they share exactly the same genome. And the fact is when they're in the locust form, the swarming behavior, the gregarious form of the locusts, generate the conditions that maintain the insect in the locust form. So unless you remove them from that environment, take them back to the lab for a little while, a generation or two, they turn back into these things. But nobody sort of knew that till fairly recently. So this is another example of, a little different example of where you have a common genome that you can't understand the expression of at all, really, unless you understand things in terms of what we would, I guess, normally think of as environmental and social properties. And the question really is, where is the inside and the outside of this system as well? So that we can understand this thing from the point of view of I mean, where's the biology of this, and where is the stuff that's outside the biology of this? And there's other examples. I mean, Toxoplasma gondii creates a relationship between cats and rats and mice, and the parasite that changes the behavior of the mice so that it makes them more available for cats to eat them actually changes their brain chemistry. And it enhances the survivability of, the parasite. And so the question really is there, I mean, this is a different thing than this, is like, these are 3 different collections of genes, and they act like a system, not unlike a lot of other sort of vector-borne diseases, but this one actually is strange in the sense that it changes the behavior of it explicitly changes the brain of one of the organisms involved, so that the information and signaling aspects that are being mediated by this parasite have to do with the scent attractiveness or unattractiveness of cats to rats. And that's that's many steps away from the parasite genome, or for that matter, from the rat genome. So there's, I guess what I'm saying is that these are examples, and I'm going to make some more, of what I'm calling massively interacting systems, and that means, plainly, that there's you, and then there's whatever the household is that you're a part of. I mean, a household doesn't have to be a family, it can be a family, but it could also be, I don't know, a prison cell, it could be a dorm room, it could be a barracks, but whatever your household is, you have those interactions, you have work interactions, you have lots of other kinds of things, and simultaneously, you're interacting in all of these media. And the interaction structures are in those, they propagate effects back and forth around, and they seem to maybe be relevant, and the question is, how do we take these things into consideration in any kind of meaningful way, and what are the bounds on being able to do that? Oops. So the example of manufacturing B12, you don't make any significant amounts of B12. Bacterium and the microbiome, of course, make B12. They don't have your genome, they act like an organ, and so it's not clear who you are in this case. And in fact, because there's this matrilineal aspect to these things, it's not clear who you are even in location and time. And so, again, there's lots of interactions where it's the among aspect of this signaling, so on, not necessarily what we normally think of as within, that is the pertinent aspect of biology. And this begins to lead to what I'm meaning by explanatory theories that are informational in character, not so much, say, biochemical in character or biophysical in character. And that I mean, they're embodied, these informational processes are embodied in chemistry, they're embodied in other things, but the fact of the matter is the explanatory theories, I'm hypothesizing here, are possibly they're information related. And so I'm going to talk about an example of what I mean by that outside these other rhetorical sort of questions. But first I have to explain what a distributed algorithm is. And I'm going to do it by an example. So there's different kinds of views of distributed algorithms. I mean, you can just have a lot of stuff, algorithms that pass information back and forth, and of course those are distributed and those are algorithms. But I'm talking about something a little different. So I'm going to give you an example. So this example is an early example. It's a very simple to describe example very initially. I mean, the seminal work was very tricky to deal with analytically, but and we don't still completely understand these things, but it's a common thing that's used in for example, distributed high-performance computing and other kinds of issues. But let me just tell you what it is. So this is due to a guy named de Groot. It's a distributed algorithm for finding maximal values on node values or edge values in graphs. So you have a graph, it's an arbitrary graph, it can be as big as you want it to be, just any kind of graph you can imagine, as big as this room, as big as this city, as big as this planet, lots of little edges, things everywhere, and every vertex has a number on it. And your question is, can you find the biggest number? And you're on a graph, so how do you search this graph? So it turns out that in order to make sure that you don't keep revisiting the same one all the time, because after all there's a lot of them, you want to be efficient, you want to get through them. You have to sort of keep track of the paths you're on in this graph, which makes it intractable from a computational point of view. And intractability is brought up a lot of times. I'm going to tell you my two-penny version of intractability, which is a much better one than usually described, but it's this. All intractability means, it doesn't mean you can't find any solution. It means that you can't find a solution that's okay for every situation. That's what intractability means. Computational intractability. So if I say something's NP, a situation, a kind of problem is NP, it means that there is no solution for all problems of that kind that'll work for all problems of that kind. And so then the industry of looking at this kind of computer science is to make this thing into dichotomies and find those classes where you can. So, this pathfinding problem that comes up in de Groot trying to keep track of what all the vertices are you're passing by is NP, which means you could probably find special case solutions for certain kinds of graphs, but there's no solution for all of them. So the problem is intractable. So the question is, yeah, but we still have all these graphs we have to find maxima for. So what do we do? Is there any kind of way to make this reasonable? And so de Groot envisioned a way that in parallel, or as close to in parallel as you can, let's say we can do it in parallel. We have 1 billion processors and 1 billion vertices, and we're just going to put a vertex on every process, or every whatever, you know. So we're going to look at them in parallel. So how are we going to do this? So we still don't know which one's the maximum, we just read them. And so what happens is this in de Groot's algorithm. Every vertex looks at its neighbors, its immediate neighbors, and replaces its value with the largest value of it or its neighbors. And you do that in parallel, you just pulse, you do it in rounds. And in order log n rounds, with probability that you can set by how many, the criteria you have for how accurate you want this to be, you'll read the maximum number. You can also do the minimum number, but you can't do the 5th largest number. But sometimes you don't need the 5th largest number, or the 2nd, or whatever. I mean, they get harder and harder, right? So, this is an example of a distributed algorithm. What's important about a distributed algorithm is that you cannot find the solution, you cannot look at any node and understand what this thing is doing. You can only look at the interaction among all these things to understand what's going on. And you can understand that by looking at the genome in isolation. And so the question is whether there's any relevance biologically to these kinds of questions. And so I'm going to make another example. And it's called graph matching. So here I start with the graph. And the only reason we keep having graphs is graphs are convenient abstractions for interactions. So if we know there's an interaction, we can replace it with an abstraction that gives it, says this interacted with that, and we put an edge on it, and we label what the interaction was on the graph. That's the only reason we keep talking about graphs. That and these are nice examples. In graph matching, what you do is you have a given graph, and what you want to find is what, in technical terms, it's called a maximum match. You want to find the maximum number, the maximum subgraph of degree 1. And what that means is you want to find the maximum number of pairs. So you start out with some complicated graph, and what you wind up with is nothing but pairs. And you want the collection of pairs that's the maximum number of pairs. Because sometimes if you pick one pair, like so if you have like a thing that's shaped like this, if I pick this one, then I can't pick these because this is already used, right? So you can see that the choice that you make, and so this is also an intractable algorithm in general, although people use it for things. So what I'll say is this, is that when, so mate selection has an abstraction as a graph matching problem. It says we're going to make these pairs, and there's some selection criteria, and you wind up with pairs. And that problem, as an analytically closed form solution, is undecidable, but if you set it up as a graph matching problem, and you understand what the properties of the local maps are, you can understand what the efficiency of these matches are under some sort of criterion. You could make the criterion whatever you want them to be. And that mechanism is what sort of managed the genome before anybody knew what a genome was forever, right? Graph matching. So to understand what this is, there has to be an offer and there has to be an accept. So that means this algorithm doesn't exist. It's a little different than de Groot's algorithm. You see, that one had the same thing on all the nodes. This has different things on different nodes. But you have an offer and an accept pair. And to understand how this plays out into finding the maximum subgraph of degree 1 has mathematical structure, and it causes, depending on what the local maps are, which have no idea what the outcome is generated by them, it causes the pairings that wind up. Causes them, is what I'm arguing. It's the cause. The efficiency with which it works, all of that, it's the cause. So that these, oops, I haven't backed my machine up in 1,130 days on my time machine disk because I threw the disk away a long time ago and I can't make that message keep coming back. So the point that I'm trying to make is that when you're, this is really irritating, right? So the point that I'm trying to make is that, it's a simple point, but it's one that I belabored here, is that if we want to use computational and mathematical methods to understand systems that are this sort of thing, where the causal structure, you can't find it on an individual item, it only exists among them, and it exists among them in layer after layer of media, is a natural problem kind. It is not a composed federated simulation. It is not something that necessarily has a descriptive causal form outside the analysis of the process itself. is a form of information biology. And it's really relevant to things like understanding the interplay between pathogens and immune systems and microbiome circuits and all kinds of other things which aren't inherently social, or at least you wouldn't think of them as social, but they are massively interacting in very similar ways. And so this thing that I'm calling the inside-outside problem is I really can't tell when I'm sort of in you or out of you, because if I have to include your matrilineal line to describe you, I don't even know when you are, much less where you are. And you interact in ways that are relevant, and again, to apply these computational methods to these kinds of systems goes beyond, I'm asserting, the way we've used mathematical and computational methods till now. It's related to the way we do it, but it's different, and it deserves a look. It deserves a look in problems like the ones that, as far as I understand, having not been at this thing, but in terms of the general subject topic, that are relevant to this subject topic, relevant to understanding the immune system. And beyond just understanding the immune system alone, understanding the process of studying the immune system. So if we use these kinds of representations to generate plausible, at least hypotheses, and then go into the process of measurement in the lab to further refine the representation in the model and so on. And the model is really a form of observation that we have inserted into the experimental cycle in a way to understand systems that are bigger than we can just understand in a straightforward way on sort of a measurement by measurement basis, or with other kinds of theoretical structures that are sort of more tractable and compact and easy to get in your head. And so Joseph's program, the MIEP program, does that sort of thing, where the computational modeling is generating hypotheses that are then tested in the lab. And that is also a process of using information systems and this kind of a systems approach to understanding systems. So that's another version of information biology, which is, of course, using information technology to study biological systems that are of these massively interacting kinds. And anyway, so there's a lot of other examples, obviously. I happen to really like the mate selection example the most. I really like the way that it results in a structured view of how this comes out, where you can understand it by studying any particular node. I think this is a really important thing to notice from a theoretical point of view. I don't think this is necessarily going to be uncontestable, what I'm saying. I don't think it's going to be anything that's going to make everybody super happy that has a different perspective, and I don't necessarily think it's in every example I gave you in every detail correct. But I do think that this notion of information biology, where causal theories are informational, is important. And I'm going to end with a couple more examples of situations where I think that's important in how things change, not just in biology, but in things like other sorts of data sciences that we're involved with that are related to other kinds of things like epidemiology or something. Or policy making generally, big data. So I think that it is pretty plain that here's an example. So if the example is, what happens when you swipe your credit card in one of those swiper machines? And you give me a figure, so we go to NCR, and we go to Cisco, and we go to all these different places, and we get a collection of procedures that occur when you swipe your credit card. And those are facts. That's what happens when you swipe your credit card. Then those facts, in the form of those procedures, I claim that's data. It's the data type process. So it's not int or real or something, but it's a data type. So now if we're going to take other kinds of data and we do things to them to impute things from them, we can regress them. We can do all kinds of things. We can stick them in Bayesian style methods and other kinds of methods. We can test them. We can characterize them with distributions. But with procedures, basically what you can do is you can compute them. And so if you want to integrate them, if the question is what happens with this procedure, and then what happens, here's another procedure, what happens to the traffic light? If you want to know what's going on with the traffic light, you could measure traffic, or you could ask Siemens to give you the traffic light scheduler. And that would be a fact, it would be data, it would be procedural data. There's a lot of procedural data. And the ability to deal with procedural data as procedures is a direct function of the appearance of all these big computers. Because we really couldn't do very much with billions of procedures till we had computers. But now we do, and so when we're going to integrate this information, it's more than just saying, oh, I have a model and I have some data and I'm going to calibrate my model with the data. If you have a lot of procedures, that's not a model, that's a data integration problem. I mean, it could be a model, and you're going to use simulation technology to compute them and interact them and so on, almost certainly. But it doesn't mean you're necessarily best to think of it as a model per se. You could make a model with it, just like you can make a model with other kinds of data. But the fact is that the integration of this information has all these procedures in it, which means that the causal explanation, so now if I start out with a procedure, this is what NCR tells me happens at the little doodad when you do this thing. That's what NCR tells me, that's the procedure. Okay, so now what I do is I have to compute this, so I don't emulate it, I don't just take that thing and stick it in, I write an algorithm that I claim estimates that procedure, or approximates it, or something. The mechanism I would use to show this, I could, of course, collect a lot of data on swipers and compute this thing and compare the data, but what I could also do is use a proof theoretic method to prove that my algorithm converges to that procedure. I could represent that procedure as an algorithm and I could prove something about that algorithm. And that would be a validation of procedural data. And that means we're in a completely different world. It means that what's going on about what makes it valid has to do with its mathematical, its informational properties. And so in a world where we've included all this procedural data, and we're sticking it all together, and some of it's inside and some of it's outside and so on, and we have distributed algorithms, just to get back to the point here, is that the concept of what's going to happen to what we understand using simulations is more than just computing a bunch of models and going around validating it against conventional data sets all the time. Although there's an element of that that will never go away, it's extremely important, but that's not what's really exciting about using all these informatics techniques for modern science. And so all I'll say to end is that just like I'm not sure that the honeycomb, I'm not sure which side of the equation the honeycomb is. I'm not sure if it's a biological object or a technological object or a trace of an interaction or what. I'm not sure exactly. Maybe it's all of those things. You have to pick which question you're asking. But when I look at cities and I ask, or places outside cities, I look at human habitation, I look how we populate the earth, and I look at how that impacts health and other kinds of behaviors. And I'm not sure where the biology stops. I'm not sure what those organisms are. And I don't think from the point of view of public health policy or fighting contagious diseases or looking at the social implications of habitat design and obesity, or a number of other things, that it's all that valuable to go about carving these distinctions up very finely. I think if we have these kinds of tools and techniques and we have this perspective, I think we can make a very disruptive impact on how to go forward using the kinds of technologies that were very disruptive when they appeared and what established this institute, and what made the post-Sanger period disruptive. I think information biology and this passing of things into massively interacting systems and understanding how they impact everything from what we do in the lab to public policy is an important integrating construct and concept, and it's what I hope we can sort of organize ourselves around here, but it's also what I would really like to, if it's possible, work with all of you on and trying to figure out what I just said. So, so thank you.
We have plenty of time for questions, discussion. Sure.
Yeah, I love the concept. I think I totally get about the crossing the boundaries and so forth. So I have a question about how one goes after that in a practical sense. With respect to the kind of data that might be involved in the different places. So the locust, the outside, the cat, the mouse, the rat, because in the way we tend to construct models in biology, we sort of have to set up a whole study and make sure we get enough data that we cross all those boundaries kind of in a coordinated way, let's just say. And what I'm worried about, how do you tackle this, is what I would call missing data or sparse data, that you actually haven't done a study with all the different parts, and so you have some data over here and some data over here, so that really weren't developed out of the same study. How does one aggregate that then?
Right, okay, so
It's like just very sparse in terms of if I put in one big matrix of all the possible things, most of it's not there.
right, and that's the general situation. So did everybody hear the question, or should I? So it basically said, so there's lots of data sources. So the way we would approach a big interdependent question, like, for example, Gandhi, say, is it has lots of bits and pieces. All of them are partially studied. None of them have been studied together, and you want to understand it holistically. And so how to use all this partial information to generate a better understanding that includes all those pieces. Is that fair?
Perfect.
Okay, so, right, so the PCAST talk that I didn't give, but that I sort of alluded to and I sort of weaved around in places of it here, was at a big data in science and decision-making presentation for PCAST. And that's exactly the generic question that's asked, is if you have unstructured data, what do you do with it to understand the world? And what does that have to, does that change how we think about science and so on? Well, okay. So I don't know if it's going to hold up for all eternity, but right now, so in the network dynamics laboratory that Joseph works with, that's at our institute, one of the main program structures is something called synthetic information platforms. And the whole point of this is you build a middle layer that interacts with the unstructured world and produces a structured synthetic environment. And by structured synthetic environment is something where, so we don't really have you in it, we have avatars that are very you-like, but not you. But anyway, so let's say we have you. And this is you in your family or something, and this is you at work, and this is you shopping, and there's time series of these things that are going. And so what you are is this unencapsulated thing that is everything in every one of these media that's labeled you. So you're this hyperedge that goes through this thing, which means you are an address structure that is associated with the thing, the you thing, in a data library. So the point is to produce this data library that has this information and that's searchable. So there may or may not be enough information to draw the conclusions you want, but you're going to be able to figure out what you don't know or what's plausible or how it can go. And then you do an experiment. And this is what I was talking about on how this stuff can interplay with the experimental method to help fill it out, to help tell you of all the things that are possible where you are. So let me tell you one, there's a lot of problems with this. Let me tell you two of them. The first one is Simpsons paradox. Okay, so Simpsons paradox is in statistics. It's an annoying paradox. It's also called the ecological fallacy. And what happens is, I have to draw a picture in the air. So I'm going to draw a picture in the air. So here's an axis, here's f of x and x. And investigator 1, for whatever reasons, collects these two data points. And they're arranged this way. Investigator 2, with no communication to 1, for no other reason, completely different everything, collects same f, same x, but everything's different. And it's over here, but it also has this. So now, if you look at this and you have the right semantics, you can say, in both of these cases, as x increases, things go down. So you can argue that they go down. On the other hand, if you don't know what you're doing and you just do it naively and you just have your regression algorithm that just syntactically runs at this thing, you'll fit this direction. So you'll say, oh, well, the relationship is it's increasing. And it turns out that you can make it do anything you want to. So the use of unstructured data has this problem. So that's one problem we have to be able to deal with. The solution to this problem inevitably includes the incorporation of semantics and purpose and details. Okay, that's which I'll leave at that. What was the second problem? Oh, the second problem is branching. So in 1980, there was absolutely nothing in physics or economics or anything else, psychology, sociology, anything, law, that kept me from buying Apple stock at $14. I was there, I could have sold my car and my house, and I didn't have much money, but I could have done whatever I could have done and bought Apple stock at 14. But I didn't. And the world branched. Just because it was possible, completely lawful, doesn't mean I did it. And the world branched, and now I'm wherever I am, and I can't decide to go buy Apple stock at 14, which means there are places the world can go, and it's best not to think of these as distributions, because think of how many branches we're talking about. Especially from the point of view of these constructive methods where you compute. So the trick is to stay on the branch relatively closely to the branch you're on. But these two things are related. The two things, the Simpsons paradox and staying on the branch you're on, are related, and they're both associated with context and maintaining a contextual relationship, which is a measurement, data, observation relationship with the world you're in, which fits beautifully into an iterated provisional scientific paradigm where you operate these systems in this way. So what I'll say is this. We think that our synthetic information platforms in generating these contextual, provisional, observed realities in interaction with further observation and incorporation of the data type process, as well as and massive amounts of computation, help us stay in some sort of hull that remains relatively tractable and allows us to do science. And it amounts to staying in the world that you're actually in instead of something that's completely plausible and lawful in every sense, but that isn't where you are.
Thank you. Other questions?
Yeah.
Is there an application available right now where you can, where they automatically extract data from publications and then make connections between each publication? So like if I observe the same phenotype of mutation, but then there are some other independent scientists that also do the same phenotype. And then there's an application that can connect the two phenotypes and then see whether or not there's connection between the two different mutations. Is there applications like that?
The short answer is that there's a lot of energy in another branch of what I would call information biology, that this is tools for sharing that are related, if not exactly what you're talking about, closely related to what you're talking about, and ultimately the goal is to get to where you're talking about. And this has to do with the management of biological big data, and these portal systems like Patrick and the other BRCs have elements of this in them. MIEP has an element in it of this in its area, which is a collection of literature and other data outside what you used in your lab and informing yourself with the model and then adding the information that you collected in your lab. It's a little different, but it has this aspect to it. And there's another portal in the Network Dynamics Laboratory called SciNet, which is an NSF portal for network science, where if you take any NSF funding for network science, then your results, the graphs you generate, or the networks you generate, the analysis you do, the publications you have, and all this stuff is connected and collected and becomes searchable and usable, and there's tools to horse around with it on those portals. So that one version of it has to do with the evolution and the maturation of these portals, which is a really important innovation. The first order may be a little less than the most possibly inspired approaches to things. It's largely associated with collection and provision of fairly conventional tools, but ultimately it goes to exactly what you're talking about. And all big data integration, not in biology alone, all big data integration is about this problem. That is what everybody's talking about with big data, that's the problem.
Anything else? All right, thanks very much, Chris.